Okay, so we're going to work through the problems that were assigned for classwork and homework today in case you have any questions about how we're going to proceed through them. So I'm going to start with number 3 of the stoichiometry problems that said that we had medicinal ether produced when ethyl alcohol was treated with an acid. And it asked how many grams of medicinal ether would you produce with 50 grams of ethyl alcohol if the percent yield is 85%. So we know that percent yield is 85%. And we also know that percent yield is the actual over the theoretical. So if we want to know what our actual yield is, we need to find the theoretical yield. And we find theoretical yield by doing the stoichiometry problem. And we have the balanced chemical equation, which is 2CH3CH2OH, which was written in the problem as C2H6O. And that is reacting and it is producing water, and the medicinal ether, C4H10O, which again in the balanced chemical equation was written CH3CH2OCH2CH3. This is just a structural formula as opposed to the more condensed formula. So we're going to start with the stoichiometry problem. We know that we have 50.0 grams of our ethyl alcohol, C2H6O, and we can do the calculations and determine that the molar mass of that is 46.07 grams. So we're going to use molar mass to convert this to moles. And then we're going to use our balanced chemical equation to see that for every 2 moles of the ethyl alcohol, we have 1 mole of this medicinal ether. So we're going to put 2 moles of C2H6O on the bottom and 1 mole of C4H10O on the top. And then it asks for grams, so we're going to go ahead and convert using molar mass. So we have 1 mole of C4H10O is 74.125 grams of C4H10O. And so when we go through and do all of the multiplication across and divide by the bottom, we get 40.2 grams of C4H10O. But the question asked for actual. This is theoretical. So theoretical times percent yield equals actual. So we're going to have 40.2 grams of C4H10O times 85%, and that will give us 34.2 grams of medicinal ether. And that's how we solve number 3 of the stoichiometry problems. Okay, so number 4 gives us an 8.15 gram sample of hydrogen peroxide. It gives us information about pressures and volumes. And it asks us to write and balance a chemical equation. So we have hydrogen peroxide decomposing to give us water and oxygen. The oxygen is going to be in the form of gas. Water is a liquid. This is a liquid. This needs to be balanced. So I'm going to put a 2 here and a 2 here, and now we have our balanced chemical equation. It asks for the partial pressure of the oxygen gas. Well, we know that the total pressure is equal to the sum of the partial pressures, so that would be the pressure from the water vapor and the pressure from the oxygen gas. So we know that 761.4 torr equals the pressure from the oxygen gas plus 18.9 torr. And so we know that the pressure from the oxygen gas must be 742.5 torr. Now it asks us how many moles of oxygen gas were produced. So now we're putting it all together with the gas laws from last unit. So pressure times volume equals the number of moles times the gas constant R times the temperature in Kelvin. Our pressure is 742.5 torr, but we need to convert that to atmospheres, so we're going to divide that by 760. This is now in atmospheres. Times our volume, which we're given in milliliters, so we're going to convert that to liters, 0.17623 liters, equals some number of moles, times our gas constant, 0.08206 liter atmospheres per mole Kelvin. And now we're going to multiply by the temperature, which we're given as 21.2 degrees Celsius, so that's 273.15 plus 21.2, and that's now in Kelvin. And so when we solve that, we get that N equals 7.128 times 10 to the negative third moles of oxygen. So that's our moles of oxygen produced. Now it asks what mass of hydrogen peroxide reacted. So we have the product. Now we need to work backwards to find the reactant. So we're going to start with our moles of oxygen, 7.128 times 10 to the negative third moles of oxygen. And we know that for every 1 mole of oxygen, there are 2 moles of hydrogen peroxide. And for every 1 mole of hydrogen peroxide, we have 34.015 grams of hydrogen peroxide. And so we get 0.4849 grams of hydrogen peroxide reacted. And so for our percent by mass of hydrogen peroxide in the original sample, well, we have 0.4849 grams of hydrogen peroxide reacted. We began with 8.15 grams times 100%, and we get, I believe it's 5.90, but we're going to just double check. Oops, sorry, it is 5.95%. So that's how we solve number 4. So those were the 2 from this section that I asked you to do for homework. So let's go ahead and move on to the acids and bases, the titrations. So we have potassium hydrogen phthalate. We're told that potassium hydrogen phthalate is a monoprotic acid. And so we know that our net ionic equation, since this is a monoprotic acid, is going to be 1 hydrogen ion reacting with sodium hydroxide, so 1 hydroxide ion to form water. Net ionic equations are very, very helpful when it comes to complicated compounds like potassium hydrogen phthalate. And then it asks us to find the molarity of sodium hydroxide when we're given a mass of potassium hydrogen phthalate and a volume of sodium hydroxide. So if I have volume, I know that molarity equals moles over volume in liters. And so if I have a volume and I want to know molarity, I need to find the moles of sodium hydroxide. And so I'm going to begin with what I know, which is the 0.212 grams of potassium hydrogen phthalate. And it gives me a molar mass of potassium hydrogen phthalate, which is helpful because it doesn't even give me a formula for potassium hydrogen phthalate. So we have 204.22 grams of potassium hydrogen phthalate per 1 mole of potassium hydrogen phthalate. And we know that 1 mole of potassium hydrogen phthalate, because it tells us that it's monoprotic, is going to give us 1 mole of hydrogen ions. And for every 1 mole of hydrogen ions, we're going to have 1 mole of hydroxide ions, which come from the sodium hydroxide. So 1 mole of hydroxide ions comes from 1 mole of sodium hydroxide. And so we work through that whole problem, and we get that we have 1.04 times 10 to the negative third moles of sodium hydroxide. We want molarity, so we're going to put our moles over our volume. So we have 1.04 times 10 to the negative third moles of sodium hydroxide divided by 0.03500 liters of sodium hydroxide solution, and that's going to give us 0.0297 molar sodium hydroxide. So we needed to recognize this basic net ionic equation, and we need to recognize monoprotic means that this is going to be 1 mole of hydrogen ions for every 1 mole of the acid. And from there, it's just a simple, straightforward stoichiometry problem. So that's number 1. I also asked you guys to do number 4. So number 4 says that we have 0.543 grams of an unknown monoprotic acid again. And it tells us how much sodium hydroxide was used to reach the endpoint. So again, because it is a monoprotic acid, we know that our net ionic equation is hydrogen ions plus hydroxide ions yield water. And so it asks us to find the molar mass of the acid. Well, molar mass we know is grams per mole. And I know the grams, I have 0.543 grams, so I must need to know the number of moles. So I need to find the moles of my unknown acid. So I'm going to start with what I know. I have 41.21 milliliters of sodium hydroxide. And I know that for every 1 liter of sodium hydroxide, I have 0.150 moles of sodium hydroxide, because it told me that it was 0.150 molar. And from my balanced chemical equation, I know that for every 1 mole of sodium hydroxide, I have 1 mole of hydrogen ions, and because it tells me that it's monoprotic, I know that for every 1 mole of hydrogen ions, I have 1 mole of my unknown acid. And so from this, I get that I have 6.18 millimoles of acid, which is 6.18 times 10 to the negative third moles of acid. And so I'm going to take the mass and I'm going to divide it by the number of moles. So I have 0.543 grams divided by 6.18 times 10 to the negative third moles. And that gives me 87.8 grams per mole. So I've now found the molar mass of 87.8 grams per mole. And if I look at the chart of available choices to determine the identity of the acid, the closest one that is monoprotic is butyric acid. So I'm going to make the assumption that I have butyric acid. Okay. The last one that I asked you guys to do was number 5. So the first thing we're going to do is take a look at our meniscus, and I've drawn a line across here from the bottom of the meniscus. This is 43, 43.1, 43.2, 43.3, and I would say that's 43.32 milliliters. It's a little bit fuzzy on there, sorry. So we have 43.32 milliliters. That's my judgment of where that meniscus falls. So for A, I would say 43.32 milliliters. So A, this is 5A, is 43.32 milliliters. So the total volume of solution is the ending volume, 43.32, minus the starting volume, which it tells me was 1.07 milliliters, and I get 42.25 milliliters of sodium hydroxide. So then C asks me to calculate the molarity of the hydrochloric acid solution. Well, I know I have 42.25 milliliters of sodium hydroxide. And I know that for every 1 liter of sodium hydroxide, I have 0.150 moles of sodium hydroxide. And I know that for every 1 mole of sodium hydroxide, I have 1 mole of hydrochloric acid. And so I can figure out that I have 6.338 millimoles of hydrochloric acid, and I know that I have those 6.338 millimoles in 25.00 milliliters, and so the millis cancel out and I just have moles per liter. And that gives me 0.254, whoops, 2535. Nope, I was right the first time. 0.254 molar hydrochloric acid. This only has 3 significant figures, so my answer can only have 3 significant figures. So that's how we get the answer for number 5. I hope these are helpful. If you have questions, please let me know.